Assalamualaikum and greetings to everyone. My name is Zulfakar Saadi from the Center for Environmental Sustainability and Water Security IPASA, University Technology Malaysia, UTM. Today, I will present our research entitled Selection of Meteorological Rain-Based Drought Indices and Trend Analysis using CHIPS Satellite Precipitation Product in Johor River Basin, Malaysia. This study aims to evaluate the performance of 7 rain-based meteorological droughts, namely Rainfall Anomaly Index, Standard Precipitation Index, China Z Index, Modified China Z Index, Percent of Normal, Decile Index, and Z-Score Index. Drought is complicated by the fact that it is difficult to predict impacts. Large area slowly develops, and its presence is normally only detected after weeks or months. This is the reason for the slow response to drought, which causes the efficacy of drought protection to be very low. Although there is no universal definition for drought can generally be defined by lower levels of rainfall than what is considered normal rainfall in a given climatic zone. When this phenomenon lasts for a season or longer, scarce rainfall will be unable to meet the needs of the environment and human activities. Drought also can happen due to the shortage of food or water due to improper management of water supply. There is no universal definition of drought because drought is site-specific and case-specific, as it needs to consider the local climate influence and the purpose of its application. The regional extent of droughts is defined by each region, which has specific climatic characteristics because the seasonal influence, form, and amount of rainfall differ widely among each of these places. Within this context, in a tropical humid environment such as Malaysia, where precipitation is normally evenly distributed throughout the year, a drier than normal period of several weeks or months may constitute a drought. On the other hand, in persistently dry areas such as the Sahelian region in Africa, droughts are recognized only after 2 or more rainy seasons without rain. Therefore, different data requirements, approaches, and indexes have been used to suit the local drought assessment across the world. Here, drought must be viewed as a condition that is relative rather than absolute. Droughts are commonly classed as meteorological, agricultural, hydrological, ecological, and socioeconomic, and they differ in terms of frequency, duration, severity, and spatial extent. In addition, drought indices also quantify rainfall deficit under multiple timescales to allow for temporal flexibility in the evaluation of the impact of droughts in relation to water supply. On a shorter timescale of rainfall anomalies, changes in soil moisture content already can be observed. Meanwhile, changes in the stream flow, groundwater, and reservoir storage are observable over the larger timescale of rainfall anomalies. For this reason, calculation of drought index was made for 1, 3, 6, 12, 24, and 40 month and 48 month time scale. For meteorological droughts, a 1 or 3 month time scale was generally used. For agricultural drought ranging from 1 to 6 month time scale, and for hydrological drought analysis and application between 6 to 24 months time scale. For more may be applied. Considering the regional context of the drought, a number of drought indices have been developed based on meteorological parameters like precipitation and air temperature. And also there is a hydrological parameter like discharge and river flow and water level. Because none of the approaches now in use can be deemed universal, emphasis should be given to the right selection of drought indices. This is due to the occurrence of drought, often the result of many complex factors interacting with the local environment. Thus, the assessment of drought is site-specific and case-specific because it needs to consider the local climate influence and the purpose of its application. Therefore, different data requirements, approaches, and indexes have been used to suit the local drought assessment across the world. The method selection is mostly dependent on regional factor, data availability, and the approach's capacity to best estimate the incidence of drought spatio-temporally as well as its variability. Thus, independence from geographical and characteristic of the climate at the affected area, including extreme climatic condition, physical foundation of a method, and calculation simplicity would be the main criteria for the selection of the best drought analysis methods. Many drug indices have been established and utilized over the years, either employing a single variable, integrating numerous factors, or mixing two or more indices. For example, we have PDSI, SPI, DI, Desal Index, CZI, Modified CZI, RAI, ZSI, Z-Score Index, and PN, among others methods. In the case of Peninsula Malaysia, droughts are most frequent to happen during the southwest monsoon, with a notable case in 1997-1998, when the relatively dry condition was worsened by the El Nino event. According to Yusof et al. 2014, the northwest and southwest parts of Peninsula Malaysia are more likely to experience drought during a dry event and receive less rain during a wet event. However, relatively few papers on drought identification and characterization has been published across Peninsula Malaysia. This spurred the need for drought assessment in the Johor River Basin, located in the southern region of Peninsula Malaysia, where agriculture is a major economic sector and where serious drought-related damage have been reported in recent years. Besides, highly valuable ecosystems are situated along the Johor River Basin, and their survival is highly dependent on the amount of rainfall and natural flooding frequency. Therefore, the impact of drought on this environment should be considered. This will also provide an excellent opportunity to investigate the adequacy of drought identification methods that are commonly employed for drought analysis in the case of Johor River Basin. The aim and objective of this research is due to high uncertainty and disagreement on the application of the various types of drought indices, more research is needed to close the gap, particularly on local scale or basin scale. So in case of Johor River Basin, rainfall plays a major role in governing the local climate condition, which subsequently determine the amount of rainwater received over a particular area due to its high spatio-temporal variability. Within this context, the methods used for drought identification and monitoring in Johor River Basin for this study consider rain-based meteorological drought indices, because rainfall has a major influence in governing the local climate and inadvertently the occurrence of drought. In this study, 7 rain-based meteorological drought indices, namely RAI, SPI, CZI, MCZI, PN, DI, and ZSI, are used to evaluate the meteorological droughts in Johor River Basin, which face increasing water scarcity issue in recent years. These indices were selected because they assess the meteorological drought in various timescales. It also has been found that meteorological rain-based drought indices give a good correlation in determining other types of drought, such as hydrological droughts. Besides, these drought indices are based solely on rainfall for their calculation, and they have been successfully applied in various climatic regions for the spatio-temporal representation of droughts. Besides, the reliance on rain-fed irrigation for agriculture activity, which now accounts for more than 60% of the total basin area, further emphasize the importance of rainfall in determining the drought condition in Johor River Basin. Water conservation and water supply are also highly dependent on rainfall throughout the year. This research finds it novelty in terms of its relevance to simulate drought occurrence and robust methodology to select the best drought indices to be used over a basin scale in the case of Johor River Basin. Compared to other studies that rely on station data, the usage of CHIPS dataset will improve the spatio-temporal drought assessment over a basin scale study of Johor River Basin. The previous study mainly focused on a larger regional scale over Peninsula Malaysia, which only used 1 or 2 drought indices in the research. There is also a low number of station data with a shorter period employed in the previous study, catering only for the need of broader regional scale and event-based drought occurrence. This does not necessarily reflect the spatiotemporal pattern of basin-scale drought condition. Therefore, there is a constraint in terms of employing other drought indices due to the besides, there is a constraint in terms of employing other drought indices due to the limitation and unavailability of other parameters such as river flow, temperature, solar radiation, and so on within your river basin. There is also a limited number of drought indices being assessed in the previous study. Therefore, the study takes the initiative to evaluate 7 rain-based meteorological droughts, namely RAI, SPI, CZI, MCZI, PN, DI, and ZSI. So the study area is Johor River, which is the main river located in the southeast of Johor, the southernmost state of Peninsular Malaysia. The river is 122.7 km long and has a catchment area of more than 2,600 km square. It is located very close to the equator, with elevation ranging from 3 to 977 meter above mean sea level. The Johor River Basin spans extensive spatial domain of complex terrain with a high variation of rainfall climatology. The local climate was spatially varies because of the peculiarities of local atmospheric circulation and sea currents in in the coastal zones, orographic impact, and geographical location. Based on the CHIPS dataset, the average annual rainfall for the period of 1981 to 2020 in Johor River Basin is 2,515 millimeter, with the highest total of 3,122 recorded in 2007 and the lowest total of 1,890 millimeter recorded in 1997. 73%, which is 79 grid point of the area in Johor River Basin, show significant changes in the annual number of rainy days by using a man-candle test at 95% confidence levels. The northeast and southwest monsoon, which directly influence local and regional atmospheric circulation, stimulate the seasonal development of meteorological events in Johor River Basin. The northeast monsoon, which lasts from November to March, are notable for their rapid increase in rainfall amount due to the Borneo vortex and cold surge, especially toward the end of the northeast monsoon. The intensity and frequency of rain events were usually enhanced. The Johor River Basin water system is well equipped for large-scale irrigation network. It is one of the major oil palm producing area. The Federal Land Development Authority (FELDA) and the Southeast Johor Development Authority (KEJORA) clear vast areas of forest in the 1970s for oil palm plantation, which now accounts for more than 60% of the total basin area. It has been reported that water scarcity has a significant impact on oil palm yield, with even a 100 millimeter deficit in soil water, resulting in a 10% reduction in fresh food yield. To maximize oil palm productivity, an effective irrigation system capable of dealing with drought is required. During the 2015-2016 El Nino event, it has also been reported that the reservoir in Lebam Dam has faced water shortage down to its dead storage zone. According to Chua, without the implementation of the barrage scheme and future scheme, the existing water resources system will be plunged into a much wider water deficit and shortfall, and water shortfall will be encountered frequently. So meteorological drought events are expected to exacerbate Johor River Basin water shortage problem due to rising population, economic growth, and climate change. As a result, more drought-related research in Johor River Basin should be performed to include valuable spatio-temporal specific input for effective water resource management. There is a difficulty in basin scale study in Johor River Basin due to insufficient observational data and inconsistency between different observed datasets. Besides, observed climate record in the station data that were usually used for climate analysis are subject to inhomogeneities and discontinuities caused by adjustment or operational setup of the station. including site location, natural exposure, instrumentation errors, or observational procedure. These discontinuities subsequently affect the mean value of the climatic distribution when one wishes to study the spatially and temporally large-scale pattern of the climate. Okay, such limitation makes spatially and temporally constant yet fine resolution graded climate data more appropriate. Therefore, 109 grid point of graded best chips rainfall dataset of desirable period spanning 40 years from 1981 to 2020 across Johor River Basin was used for drought analysis. So, thus, therefore, higher confidence resulting from spatio-temporal long-term climate data assessment can be obtained to identify changes in drought pattern. Besides, CHIPS dataset also provide a good spatial resolution of 0.05 degree to sufficiently monitor the condition over the basin. The drought condition is in Johor River Basin were assessed using the rain-based drought indices, which is RAI, SPI, CZI, MCZI, PN, DI, and ZSI. The drought index were calculated by using monthly rainfall data for time scale 1, 3, 6, 9, 12, 18, 24, 48, and 72 months. The procedure used for drought analysis are as follows. First, initially, the threshold and classification for each meteorological drought indices were defined and adjusted with a range as shown in this table 1, so that we can make a suitable comparison. Then, the intercomparison of the study meteorological indices was assessed based on their Pearson correlation coefficient by constructing a heat map based on the correlation plot to determine the consistency between the different methods in determining meteorological drought condition under various timescales. A scatter plot was then constructed to inspect the linearity relationship in capturing the dry condition. The low performance meteorological drought indices will be discarded for further analysis. Then the spatial mapping of the selected meteorological drought indices will be prepared. The best meteorological drought indices capable of detecting various drought conditions and drought frequency will be selected. Finally, mapping based on the best selected drought indices will be done to determine the spatio-temporal trend of drought in Johor River Basin. To assess the performance of the CHIPS dataset in simulating the local rainfall, the nearest grid point with the observed rainfall was compared. Initially, the spurious rainfall observed in the time series was removed from the station data. Here, the outlier was removed by making comparison with the nearby station. Then, missing data was imputed by using a MICE package from our programming package. We are using a linear regression predictive value methods. The figure here shows that the monthly rainfall validation of CHIPS dataset based on PDF and box plot with the nearby station, which show a good capability of the CHIPS dataset in simulating the local climate in Johor River Basin. There is only a slightly higher kurtosis was observed for most of the station. The correlation between drought indices was initially assessed to determine the consistency between the different methods in determining drought condition. It was found that the correlation between all drought indices for all stations show a high correlation under different time scale, more than 0.69 for R square. Correlation between all drought indices was found to increase from 1 month up to 24-month time scale before it becomes more or less constant. This figure showed the heat map based on the correlation plot for the intercomparison of drought indices based on the average correlation of all stations under all time scale. It was found that the correlation of RAI, PN, and DI with other indices show a comparatively lower correlation for the 1 to 9 month time scale. Therefore, RAI, PN, and DI would not apply for the subsequent analysis. It was also found that for most cases, a combination involving CZI, MCZI, SPI, and ZSI gives the highest correlation under different time scale compared to other drug indices. After that, we constructed a scatter plot to inspect the linear relationship between drug indices in capturing the wet and dry condition. Figure 4 show that figure here show that the scatter plot for grid point for the selected grid points show the linear and positive relationship for a combination of drug indices of CZI, MCZI, SPI, and ZSI. A good linearity was found for all cases with a square ranging from 0.961 to 0.995. The capability of CZI, MCZI, SPI, and ZSI was then compared based on drug frequency to determine their capability in detecting the presence of drug. This table shows the average and sum of the drug frequency under 3 and 6 month time scale being classified as moderately dry, very dry, and extremely dry condition. The results saw that the highest average and sum of drop frequency was given by SPI, followed by ZSI, and then CZI, and at last MCZI under all classification. It was also observed that ZSI was able to detect the presence of extremely dry condition under 3 and 6 month time scale, and both MCZI and ZSI were unable to detect the presence of very dry condition under 6-month time scale. Therefore, CZI and SPI are more capable in identifying regions that may be more drought prone than others due to its higher sensitivity in discerning the occurrence of very dry and extremely dry condition. Then the spatial map of drop frequency under 3 and 6 month time scale were constructed to spatially assess the performance between CZI, MCZI, SPI, and ZSI in determining the presence of drop. High drop frequency of moderately dry condition was observed throughout the basin under a 3-month time scale. However, under very dry condition, drop frequency was mainly observed at the downstream and east of the basin, with better detection by CZI and SPI. Under 6-month time scale, moderately dry condition were observed at the downstream area, with better widespread detection by CZI and SPI. Comparatively, SPI show a better performance than CZI in spatially detecting the presence of drug in the form of drop frequency in Johor River Basin. Therefore, SPI was selected as the best drug indices for drug assessment in Johor River Basin. Trend assessment based on the man-candle test at 95% significant level show that the drug condition is significantly decreasing in the downstream of Johor River Basin. The decreasing drought condition owing to the significantly increasing number of rainy days throughout Johor River Basin, as rainy days has become more sporadic and unpredictable due to climate change. The uses of a graded-based rainfall CHIPS dataset provide an opportunity for a better spatio-temporal assessment of meteorological drought for basin scale study. Based on the constructed correlation plot, heat map, scatter plot, and drop frequency assessment, CZI and SPI were found to be more capable of identifying regions that may be more drought prone than others. Further spatial assessment show that SPI are better tools for drought assessment and monitoring in Johor River Basin, as it has better capability in determining the presence of drought based on drought frequency. The methodology developed for comparative drought assessment in this study can be expanded to incorporate other meteorological drought indices depending on the availability of data. The result of this study can be used for comparative study with other river basin in Malaysia to improve our understanding of the prevalent drought occurrence and its impact across the different area. It can also be used as a basis for performance comparison with other types of drought indices such as hydrological droughts, agricultural droughts, socio-economic droughts, and ecological droughts, particularly in Malaysia. The results from this comprehensive rain-based meteorological drought assessment will also act as a baseline for future projection of drought condition in Johor River Basin under a climate change scenario. Thank you.